Right, we're going through the Semester 2 practice exam for methods. So the topics in particular are these last three topics we learned: stats, exponentials, and calculus. You should always aim for about 1.3 marks equals 1 minute. So try and keep on that pace as you're doing any exam. And you'll notice that the marks and minutes sort of align with that. Okay, let's get started. So these are just directly 1 mark questions. So you can literally just go into your calculator and do it. You're going to hit the option button, go across to probability, and we're going to hit 5 factorial. So that's 120. Done. Now, if you did want to work that out by hand, it was 5 times 4 times 3 times 2 times 1. That's how you do it. C64. Again, it's 1 mark, so you can get away without doing this, but 4 factorial on the bottom. And then 6 take 4 is 2, so 2 factorial there. And again, we can just sort of directly work that out. So 6 NCR4 is 15. So that's in that same options menu on the calculator. We've got some movies coming up in this next question. So how many different ways could you choose 4 movies out of these 8 possibilities? That would be 8 movies and 4 choices, C8 4. So 8 NCR4 should be your correct answer there. So we get 70. All right, next up, we've got this question here where we're looking at animated movies being required. So basically, you can have 3 options here. You can have Shrek and any of those. You can have The Emperor's New Groove and any of those. And then you can also have the B movie and any of those. All right. So pretty much the way that you can pick those 3 missing pieces is that would be C73, because there's 7 movies to choose from and 3 spots to do it. This one would be C63 and C53. Really importantly, because we have to have not Shrek in any of those spots. And in this last one, we have to have not Shrek or The Emperor's New Groove, because we've already used them up in the previous options. So pretty much what you can do is just work out all those NCRs and add them together. So 7 NCR3, if we work out what that is, it's 35. Do the same for 6 NCR3, 20. And do the same for 5 NCR3, you get 10. So the total is 35 plus 20 plus 10, which is... see what that gives us. So 35 plus 20 plus 10 should give us 65 ways. Really importantly, that has to be less than the previous amount, which is 70 ways to do it, which it is in our case. So the other way that you can do it is we can look at all real, or like all live action movies. So we've got 4 spots. There's 1, 2, 3, 4, 5. So that would be 5, 4. And we can work out what that is. That's 5. And then the total is the 70 ways to do it. Take the 5 ways that you would fail by doing it, and that would also be 65 ways. So there's 2 separate methods. Just pick one of those 2 methods. Okay, next we've got this data about Australian exercise. So we need to decide whether the data is continuous or discrete. So yes, they've rounded the numbers, so it looks like there's only a finite level of precision, but it's still continuous, as time can be infinitely divided down, barring some weird physics stuff. But yeah, time can keep being broken down into seconds and then milliseconds, etc., etc. So that makes it continuous there. Now we want to complete this table. So we need to go into our stats menu. We just delete out any old data that we had in our calculator, and we're going to pop in all of our data just to the one really big list. All right, so I've just entered the data there. You could also count. There are 14 data points, and the calculator has 14 things, so we know we haven't accidentally missed one or something. We're going to go set. Now, you will often have this set as list 2 here. Since we've got a big long list of numbers, we need it to say 1 instead of list 2. If you're using a frequency table, you would keep that as list 2. Then we hit F1 for 1var stats, and that gives us some wonderful statistics. Okay, So 3 significant figures. So we're going to go 3.99 for the mean. So that was X bar on the calculator. We can also get the standard deviation. Now this is exercise of Australian teenagers, and we've surveyed 14 people. So I don't think we have the population. We're going to have the sample. So that's SX on the calculator, 2.91. And then this 5-number summary you can get if you just scroll down a little bit. So that would be 0 to 3.5, 5.5, and 10. When he completed the table, we used the sample SX because we only had a sample of 14 people, less than the total number of teenagers in Australia. So I'm assuming that's less. I know probably more than 14 teenagers. Okay. Would this data accurately represent the amount of exercise? So giving 2 reasons for your answers. Okay, so there's a couple points to make here. We surveyed the PE class. This is a biased sample. PE students may like sport better and do more exercise. Especially since this is a year 11 PE class, they would actually be picking PE at this point as well. Next, we've got the actual town itself. So Kimber is a country town. Kimber is a country town. May have an impact on the physical activity levels. So you may be either more interested or less interested in physical exercise and sport, depending where you live. So that could affect it. We only looked at year 11 students. Younger and older teenagers may be different. So they're trying to make claims about all teenagers. We've only surveyed year 11 teenagers, so that may have an effect. Last thing is we had a small sample size of 14. Generally, when numbers are getting up at around 30-ish, that's a more appropriate sample size. But that mean was 3.99. You can see if this person here, where they got 2.3, just happened to really like exercise, so they were doing like 10.3 or something, the mean would shoot way up to 4.5. So little changes in the data can have big effects on the statistics, and that means that you generally like bigger sample sizes, because then weird outliers have less effects in bigger samples. Okay, yeah, we're going to use proper notation for normal distributions in this question. Let X be the mark of a student on the 2023 methods exam. Okay, then we need to give some notation here. So X is distributed normally. We give a mean of 60 and a standard deviation of 12. Notation-wise, it's good to put a little squared symbol up there. When people are talking about normal distributions, they like to talk about the variance instead of the standard deviation. Variance is 12 squared. So we can calculate the probability. And long and the short is put a squared above that little and bit on your normal distribution. We can calculate the probability. So we're looking between 48 and 72 in normal CDF. Standard deviation was 12 and the mean was 60. Okay. Right, so our calculator gives us an answer out here. We just got to pop that in. So the probability that we're between 48 and 72% roughly equals 0.683. So 3 significant figures there. Calculate the probability they get less than 43.3%. Roughly equals, so that is, we can just go to normal CDF. Your upper is going to be 43.3 and your lower is just minus and then a whole bunch of 9s. So if we do that, 0.0820. 0.0820. So 3 significant figures there again. So 8 is the first one, and then that last 0 is the third one. If 8,000 people, so basically we want 8.20 of 8,000. That's essentially what we're trying to work out. Now, when you use a percent in an equation, you have to use that decimal version. The word of always becomes times, and 8,000 is 8,000. So we need to times that probability we just got. I might use a fuller version at 0.08201168. Just to get all that precision in there. So 656. So roughly equals 656 would fail. Okay, spec mass exam is a bit different. So we're going to say let y be the mark on the spec exam. Be like a student's mark. So y is also distributed normally. It's got a mean of 55, so a bit lower, and a standard deviation of 10, so again a little bit lower. So you can imagine that maybe the spec students, they're having more trouble on the exam, but they're also more consistent on the exam, so they're less variant. The probability that we do better than this student, so 75 roughly equals, and then we'll also look at methods, and we'll look at the probability that x is greater than the methods mark, so 80 roughly equals. Okay, so we can do the methods one first, just because we still got that data rule in the calculator. So we're going to go to normal CDF. Doing better than the student, so 80 is the lower and a bunch of 9s is the upper. 12 and 60 are still that same as before. And we can calculate this probability, 0.0478. So we just pop that in. With the spec exam, we can calculate that probability as well. We'll just need to fill in the rest of our data. So 75, 10, and 55. Okay, 0.0227. So pretty much we could say something like there's a 2%, 2.27% chance of doing better than the student on spec, and a 4.78% chance of doing better than them on methods. So their spec exam was better, less chance of beating them, essentially. So the student only had 2% of all exam takers do better than them, so that's better. They're in like the top 98% versus the top 96%, if you want to think of it like that. There's another way to solve this question. You can use z-scores. That's covered a lot more in Year 12 methods, but I know some people look at that in one of the assignments we do. So if you want, you could use z-scores for that question. It becomes a lot easier. Okay, very, very good. So, moving on, we've got Pascal's triangle question. Remember, you always put 1s on the outside. And to get the new numbers, you add the previous ones. So 1 and 4 would give us 5. 4 and 6 would give us 10. 6 and 4 would give us 10. 4 and 1 would give us 5. And you could repeat that process. So 6, 15, 20, 15, 6, 7, 21, 35, 35, 21, 7. All right. Row of Pascal's triangle, there we go. And then we've got row 4. So row 4 was 1, 4, 6, 4, 1. And we want to add those up. So let's see what we get. 1, 4, 6, 4, and 1 gives us 16. You may be spotting the pattern now. 1, 5, 10, 10, 5, 1 is the next row. And we'll see what we get. 1, 5, 10, 10, 5, and 1 is 32. Make a conjecture based on your results. So sum of nth row of Pascal's triangle equals, really importantly, that's 1 squared, 2 squared, 3 squared, 2 to the 1, 2 squared, 2 cubed, 2, 4, 2, 5. That's the pattern there. If you don't believe me, you can just try one on your calculator. So you could go 2 to the power of 5. I'd encourage having all the powers of 2, powers of 3, squared numbers on your cheat sheet, just so you can spot conjectures. This one is 2 to the 0 because it's row 0. And if we check, 2 to the 0 is indeed 1. So it's 2 to the n. And I'm just going to say for all n in Z, n is greater than 0. So that means n's a positive whole number. Okay. Prove your conjecture or test it using another row of Pascal's triangle. Okay, so basically you can just use another row. Yeah, you can just use another row, and that's what we're going to do. So we're going to look at row 6. So row 6 is 1, 6, I think it's 15, 20, 15, 6, 1. And so sum is all those added together. And we can just work that out. The 64. And also 2 to the power of 6 is 64. We better actually check that that's true. Yes, it is. So these match. Therefore, conjecture is supported. Wonderful. Now, if you want a proof, the reason that I didn't directly ask you to prove this is because proof uses something from spec maths. It's called induction. If you've learned induction before, or if you want to look into it because it's really interesting, would recommend it. You can prove this using induction, and it's not too difficult. So if you want to try that, have that as an exercise. Next, we're going to use our conjecture to calculate this value. This is row 10. Therefore, this equals 2 to the power of 10. So this is really checking that you understand that connection between these numbers and the rows. So for example, on row 7, that would be C70, C71 for that number, C72, all the way up to C77. So row 10 would be with C's and 10s. Now, if you had time in your exam, what you could literally do is sit here and type 10 option NCR 0 plus, and then keep going like that, and you would eventually get 1024. Okay. Next one, a to the 8 times a to the 5. So this is where our formula sheet's going to come in handy. The index laws are all over this. So use your index laws. I'm hoping at this point you've sort of internalized a lot of the straightforward ones because they come up quite a bit. So try and remember them, but I've got them on the formula sheet just in case. Add the powers there. With this one here, we have to expand the top first. So that's minus 4 cubed, a cubed over a to the minus 2. Minus 4 cubed, so 4 cubed is 64, and it's a negative sign. If you are not sure about that, I really would encourage you to just chuck it in your calculator. Hey, look, it's minus 64. Then you need to subtract the powers. So that's minus 64. A to the 3 take minus 2. So that's minus 64 a to the 5, just like that. Okay. 3 log of 2 is log of 2 cubed, which is log of 8. This one here is log of 4 plus log of 6 squared. Take log of 3. So that's using the log laws. Log of 4 plus log of 36. Take log of 3. When you do this, any pluses turn into timeses and any subtracts turn into divides. So 4 times 36 over 3. So this is all using the log laws. So we can just work out what that is. So the calculator tells us that's 48. So we got log of 48. Really importantly, one thing you can do if you got extra time on your exam is actually type in something like this. Log of 4 plus 2 log of 6 take log of 3. And it's going to spit out a nasty number. But if you type in log of 48 into your calculator, it should spit out that same number. You know you've got it correct. And if this was more marks for this question, you could put some explanations here, like the log laws for that first bit, for example. Since it's 1 mark, I don't need that. But if it was a show that question or a multi-mark question, you would want it. Next, we've got a graph. So we're going to go and graph this. So 1,000 times, and then 0.5 to the power of, now this is x instead of t, and 5,700. I've just bracketed at the top so it definitely stays all together. We want to sketch the graph up to 14,000 years. So we're going to draw that. Beautiful graph. Actually, still got my derivative on. I'll turn that off. Okay, so let's match their windows. So their x window seemed to go from 0 to 16,000. Their y window goes from 0 to 1,200. We'll graph that. Hey, look at that. That looks like radioactive decay to me. So let's get some points in. So we're going to trace at 0, and it should be at 1,000, which hopefully shouldn't surprise you because that's the 1,000 in the equation. Let's get a few key points in here. So let's trace at 2,000. Get 784, so that would be about there. Trace at 4,000, get 614. Trace at 6,000, 482, and so on and so forth. I know it's a bit tedious connecting up these dots, but it is really important that you get the right shape. I might just skip every second point now. 10,000 is 296, so that's going to live there. And lucky last, 14,000 is 182. Now, generally what SACE will be looking for is all your key features are in the right spot. So mainly that your graph has started at the right point and sort of goes through any like minimums or maximums correctly. But essentially, if you plot some points, you can never really go wrong. If this graph had like a minimum or a maximum or whatever, you would find those points exactly and make sure they're in exactly the right spot. Last thing we need to do on this graph is actually label it. So W is that. Cool. All right, what is the initial mass? So this is W at 0, and we worked it out before. That's 1,000, I think it's in grams. Yes, mass is in grams. Estimate the half-life of carbon-14. So there's a couple things you can do. The half-life will be how long does it take to get to half? So I'm guessing about 6,000 years. That's what I'm sort of assuming. But we can get it exactly. So GSolve, xcal, 500. That's half the amount of time. Hey. So I guess it's pretty good. 5,700 is the actual amount. So T equals 5,700 years. It's actually an exact equals there. So this was, for the weight is 500. Find the exact half-life. So the weight equation looks like this. So 1,000 times 0.5 T over 5,700. What we can do is set the weight. Actually, no, I'll write it like this. So we want 500 to equal the weight. So this is like half of 1,000. Since this is a show that question for more marks, you'll be seeing a lot more notation and explanation here. So therefore, 500 equals, and we can plug in the whole weight equation. So 1,000 times 0.5 to the T over 5,700. Then we're going to divide. So 500 over 1,000 is 0.5 to the T over 5,700. So 0.5 to the power of T over 5,700 is a half. All right, so we should probably put some explanations in here. So divide by 1,000 to both sides. And we're just going to go swap sides. Yeah, if you're really keen on comparing indices, you'll notice that t over 5700 should equal 1, because this over here is a half to the power of 1 and the powers need to be the same. But I will show you the general method for solving this. So log, it doesn't matter which log you use, 0.5 t over 5700 equals log of a half. So this is log both sides. We can use log laws. So t over 5700 out the front times log of a half equals log of a half. We need to give an explanation there, so we can go log laws. Then we need to divide by log of a half, so t over 5700 equals log of a half over log of a half. I think that's hopefully explanatory. I don't need an explanation there, which equals 1. Therefore, t is 1 times 5700, which is 5700 years. Wonderful. Now, usually at this step, when you do any other question like this, the logs don't cancel out nicely like that. But in our case, it does. And that's because we're looking for the half-life. It sort of gets rid of all those nasty logs. So that's a general process. You might be able to do it a little bit quicker than that without logs, but that's how you would solve it in general. How long will it take for any amount to decay to a quarter? So we can just verify this really quickly. If we go gsolve and xcal, and we're looking for a quarter, that's 250. And it looks like it's taking 11,400 years. So 11,400 years. Okay, you'll notice that's 2 half-lives. If I try and find a half of a half, that's a quarter, so it takes 2 half-lives to get to a quarter. So this one here will be 3 half-lives. So that is 3 times 5700. I might make a note that's 2 times 5700 there. And we can work out what that is. The other way we can do it is if we go into gsolve, xcal, and we're looking for 125 would be the next one down. It's not found now. That's only because the window doesn't extend that far. So if we extend out to 30,000 years, and we go gsolve xcal for 125, you can see that it's 17,100. Let's verify that this is true. So 17,100 should be 3 times the half-life. Hey, it is, that's good. And we better give some units, so years. Groovy. All right, so next, we've got a question about carbon dating, essentially. So all this that we've been doing here, believe it or not, is actually useful. You can use it to figure out how old fossils are. So generally, like, it's supposed to have a certain ratio of carbon-12 to carbon-14, one of which decays when the animal dies and one of which stays when the animal dies. So by looking at how much carbon you have in comparison to each other, you can figure out how old things are. So basically, in a living creature, so living, we've got 1.3 times 10 to the minus 12. And in the fossil, we've got 3.25 times 10 to the minus 13. And so the percentage, these are both in a ratio to 1. So the percentage left will be that 3.25 times 10 to the minus 13, maybe like proportion. Portion left. Divided by 1.3 times 10 to the minus 12. Now, if we put that into our calculator, 3.25 times 10 to the power of minus 13. These are very small numbers. The reason is carbon-14, you have a lot less of it compared to your carbon-12, so that's why. Anyway, probably because it decays, actually. 0.25. Therefore, the fossil has a quarter of the original amount left. Therefore, it would take 2 half-lives. Therefore, the fossil is a half times a half is a quarter. The fossil is, we worked it out back here, 11,400 years old. See, this is 2 times 5,700. Beautiful. Okay, so if you ever wondered why we care about exponentials, well, now we know how old that crab was. Very good. Okay, prime numbers. What is the next prime number? That is 11. So if you're doing this, so maybe 8 is 4 times 2, so that is not prime. 9 is 3 times 3, so that is not prime. 10 is 5 times 2, so that is not prime. 11 equals, can't do it, so this is prime. So this has no factors apart from 11 and 1. So 11 is the next prime number after 7. So notice in particular, I'm showing that all the ones before 11 were not prime. And that's really important because I could have just pointed out that 13 was a prime number and then claimed that was the next one, even though I missed 11. It's really important you do that. And that's a big list of prime numbers. We want to calculate P100. So how many prime numbers are there smaller than 100? So I think if I've done it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I put them in groups of 10 to hopefully help you out. 100 cuts off there. So that would be 1, 2, 3, 4, 5, 10, and 10. So there are 25. Now this is really cool. This question gets into how we can approximate the number of primes. Log of 100 over 100. It's about 0.046. Now, if you want to calculate that, that'll be 25 times 0.0461. And that should roughly equal, so it just times up by 25 using the full version, 1.15. Calculate that. All right, so P800. So how many primes are below 800? So we can figure that out. So 800 is sort of there. So that row will be 9 because we're missing the last one. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that would be 130 there. So 139 times log of 800 over 800. The funny thing about maths is we've got all these complex problems we can solve, but something really simple like prime numbers still has a lot of mysteries around it. Okay, there we go, about 1.16. Cool. There are that many below a million. We want to calculate that. So that is 78498 times that. I've just used scientific notation, or sort of. I've used powers there to save me writing it all out. 78498 times, and then we've got log of a million over a million. Roughly get 1.08. Develop a conjecture. And now this conjecture can be a bit tricky to spot, but usually when we're looking at ratios like this, we really would like the ratio to go towards a number. So as n goes to infinity, p of n times by a log of n over n goes to 1. All right. So you can hopefully see that ratio. It starts off at about 1.15, 1.16, eventually gets closer to 1.08. I can tell you this conjecture is actually true. It's called the prime number theorem. And you can use it to approximate how many prime numbers there are in a given range. to estimate how many prime numbers are smaller than that number. So you've got P of 1 billion. There's 9 zeros, yeah. Times log of 3, 4, 5, 6, 7, 8, 9 over 1, 2, 3, 4, 5, 6, 7, 8, 9 roughly equals 1 from the conjecture. Therefore, P of a billion, I might just use, I'll use a full version. 2, 3, 4, 5, 6, 7, 8, 9 roughly equals 1 divided by that log thing. Okay, so let's see if we can get that. So 1 divided by fraction. Log of a billion. Just going to use 10 to the 9 over 10 to the 9. Hey, that number. 4, 8, 2, 5, 4, 9, 4, 2 primes. That's how many primes we'd expect roughly to be less than a billion. Now, just so we've got an idea of whether this answer is sensible, I'm going to take that answer I just got and divide it by a billion. So I'd expect about 4% to be primes. Now, earlier on, when we looked at this list, it looked like a lot bigger than 4% of the numbers were primes. Maybe like half of them were primes. But as you get to larger numbers, they get really spread out. So 4% actually seems somewhat appropriate. It's funny, as you get bigger numbers with primes, that percentage gets lower because the primes are getting further spread out. But there are still infinitely many primes, and you can prove that fairly easily, actually. Well, the proof is easy. It's not very easy to think of that proof. So yeah, there are infinitely many primes, but they become less and less dense as time goes on, as the numbers get bigger. Except, I won't get into it, but there's also this thing called the twin prime conjecture, which is very exciting in that. Anyway, look it up. F dash of x here is a 2x take 2, just like that. So what I've done is I've brought the power down from the x squared and gotten rid of the x with the 2. Okay, next we need to use this first principles. So f dash of x is limit as h goes to 0, f of x plus h minus f of x all over h. Now, in this, f of x plus h is x plus h squared, take 2x plus h. So you're just plugging h's in for the, well, x plus h in where x was. So we're going to go limit as h goes to 0. X plus h squared, take 2 lots of x plus h, take x squared, take 2x. So take f of x itself. Make sure you do that last take in brackets. It's very easy to miss that minus sign accidentally. Limit as h goes to 0, so we're going to expand out the top. So that would be x squared plus 2xh plus h squared. Take 2x, take 2h, take x squared plus 2x. Just like that, all over h. This is limit as h goes to 0. Some stuff will cancel off. By the way, if you're wondering, we're using x plus h squared. It's x squared and h squared, and you get 2 times xh. That's the middle term. So that's the little identity we've used there. Anyway, x squared should cancel off with x squared. 2x and plus 2x should cancel off, and then we're left with only things that have h's in them. So this is 2xh plus h squared take 2h all over h, just like that. And then we can pull out h as a common factor. So this is h into 2x plus h take 2 over h. Next, we're going to cancel off the h's from the top and the bottom. So if we do that, maybe we'll like factorizing. Just be really clear what we've done there. So limit as h goes to 0. So this is of 2x plus h take 2. Now that h is not on the bottom of the fraction, we can just set h to 0. So h equals 0 there. And that's f dash of x, and that also matches the answer we got before, 1 to 4. Okay, differentiate the following functions. That will be 20x to the 4. Really importantly, write f dash of x equals. f dash of x here. 3 times 3 is 9. So you get 9x, 1 less is 2. By the way, all these calculus rules are on your formula sheet as well. So that's 16x plus the x becomes a 1 and the 64 goes away. Here, the original function is 2/5 of x to the minus 3. So the derivative looks like that. And now I'd be happy with that as your final answer. If you want, you can go like that. So both those I consider correct. Y here is 4x to the half over x to the 1. So we got that. So if we look at that, we can go, that is 4x to the half minus 1. So that's 4x to the minus a half. So that's y. Now we've still got to differentiate it. dy dx is minus a half times 4, so that's minus 2x. And it's to the minus 3 halves, so it's 1 less. Again, I'd be very happy with that as your final answer. If you want, you could write it as minus 2 over x to the 3 halves, which I'd also be happy with. If you want to get extra fancy, minus 2 over x root x, which I'd also be happy with. Okay, in the year 12 exam, it has this extra bit that says don't simplify. So generally you just get the derivative and immediately stop. You don't bother simplifying it down. In this exam, I didn't put that just because I didn't want to stop you from simplifying if you wanted to. Okay, find the stationary points using calculus methods. So f dash of x is 6x squared, take 18x, that's the derivative. And we want 0 equals f dash of x. So 0 is that. Generally, when you're trying to solve things equaling to 0, you factorize it. So 6x is a common factor, and we get x take 3 there. So we're going to get x is 0 or x is 3 using the null factor law. And so the stationary points are x is 0 and x is 3. Next, we need to draw a sign diagram. So I'm just going to pop 0 and 3 on there. We need to figure out whether they're going to be pluses or minuses. So I'll show you how to do this algebraically, and then I'll show you what you probably want to actually do. Let's pick a number like, for example, 4, which is out here. So 6 times 4 would be positive, 4 take 3 would be positive, so you're going to get a positive. So when you plug in 4, you get a positive number. So that means that it's always positive out there. If we want to pick a number like 1, so that's in between here. 6 times 1 is positive, 1 take 3 is negative, so you get a negative. So that one there is going to be negative. And you want to pick a number less than 0, so maybe like minus 1. 6 times minus 1 is negative. Minus 1 take 3 is negative, so you get a positive. So that's absolutely how you do it algebraically. And it's important to know that because it can come up. Sometimes you don't have a picture of the graph. Especially year 12 exams love to ask that. So what I'd expect people actually did on this question is graphed the function, drew the function, set your window back to normal after that crazy crab question, and you hopefully see there's 2 stationary points. Well, you don't see the second one yet because it's down here, minus 30 on y. Let's see where that ends up. Then you've also got, well, sloping up, so it's a plus because it was sloping up before 0. Then it's sloping down in between, so that's the minus, and then it's sloping up after. You could also get your stationary points 0, so x is 0, y is 2, and the minimum x is 3, y is minus 25. Be aware that if these were stationary points of inflection, you couldn't use your calculator to find them, at least not in a straightforward way. Use your sign diagram to classify the stationary points. So we can already see it on the graph, but for x is 0, y is f of 0, which is 2. And you can get that just by tracing 0. And when x is 3, y is f of 3, which is, again, you just trace it 3, minus 25. So therefore, we have 0, 2, and 3 with minus 25. 0, 2 is a local maximum. And this one's a local minimum. So A, we can tell it from the graph, and B, because you're going up then down, and down then up, it sort of shows you what shape they are, maximums and minimums. Find the maximum and minimum values for 1 to 4. So what I'm going to do is just set my window to start at 1 and end at 4. And we need to check a few things. So we need to check any stationary points. So we have this one at 3 minus 25. And we also need to check our endpoints. So this would be 1 and 4. So if we trace at 1, we get minus 5. And if we trace at 4, we're going to get minus 14. So it looks to me like this is the max value, and that is the min value. So this is just purely based on the y values of those points. Minus 25 is the lowest one, minus 5 is the highest one. Next, we've got a sign diagram. Remember that this means height, and that is an x-intercept. And this means slope, and that these are stationary points. So we're looking for a graph that has an x-intercept at 0.5. So immediately we can cancel out that one. So it's going to be one of these. And we're also looking for a graph which goes down and then up and then down. So it should be that one. Okay, so it's got an x-intercept at 0.5 and it slopes down, then up, then down. So that's from F and that's from F dash. And that's enough information to tell we get it right. Okay, so that's how we do that one there. Optimization. So volume is length times width times height, which is 2x times x times h. And we also want the volume to be 400. So that's volume is 400. Therefore, I'll just write it again, 400. Well, 2xh is 400. Therefore, x squared h is 200. And that was because we divided 2 on both sides as required. Okay, so the inner surface area. So the area of the left side of the box is xh. Area of the right side of the box is xh. Area of the bottom is 2x squared. Area of the top is also 2x squared. Area of the front is 2xh. And area of the back is also 2xh. Therefore, total area is, well, it's 2 lots of the xh bit, it's 2 lots of the 2x squared bit, and it's 2 lots of the 2xh bit. If we sort of smoosh all that together, I reckon that gives us, well, 2xh plus 4x squared plus 4xh. We got some like terms there, so 4x squared is the first one, and then 6xh is the next one. And we can also, oh, we've done it, cool, yeah, well, that's good, as required. Now you might have something like terms there just for some extra explanation. I'll get to the end of the exam if I was you and then sort of go back and add in all your extra explanations. So we're going to go area is 4x squared plus 6xh. Yeah. Over here, I'm going to do this thing. I usually call it star when I do this. So x squared h, 200 from A. Therefore, h is 200 over x squared. And then we can write this as 4x squared plus 6x into 200 over x squared, because h was 200 over x squared. This is from star. Okay. So that's 4x squared. 6 times 200 is 1200. X over x squared. And then you basically just cancel off the top and the bottom. So if we just draw that in, cancel the x and cancel one of the x squareds. So that's 4x squared plus 1200 over x as required. Groovy. All right, I find the minimum surface area. So area is 4x squared plus 1200 x to the minus 1. I'm going to write it. And let's get that graphed. So if we go into graph here, we're just going to delete out the old graph here. 4x squared plus 1200x to the power of negative 1. Or 1200 over x if you want. We draw that. So we're going to go for our window 0 to maybe 20, and the area could get pretty big, so 0 to 1000 maybe. It might be a bit too big, we'll see. Hey, cool, there we go. And it appears that the minimum is 5.31 and 339. So that's what we're sort of getting to with that calculator. If you write just that down, you might get some marks. I guess you would get the full marks, considering I didn't ask you to show working out here, but quite often you want to show working out. So we want the derivative, dA over dx is 8x, take 1200 x to the minus 2. So we want the a over dx is 0. So therefore 0 is 8x, take 1200. I'm just going to write that as over x squared. There's a little trick you can use with equations. So if you ever have fractions like this, you can just times everything by x squared. So 8x cubed, take 1200. So this is timesing by x squared on both. So then you get 8x cubed equals 1200. Therefore, x cubed is 1200 over 8. We can work out what that is. So 1200 over 8, 150. X cubed is 150. Therefore, x is the cube root of 150. And if we work out what that is, 5.31. Hey, that looks familiar. Cool. So x roughly equals 5.31 meters. And you can get the area from that. So minimum surface area and the corresponding value of x. So at x equals cube root of 150, the area approximately equals, and we're just going to use that graph to get that. So we draw that. I'm going to trace at the cube root of 150 just to 150 power of a third. And you can see that it does show that minimum. The area is about 339 centimeters squared. I reckon we're in centimeters for this question. Yep, sure are. And then that should have been in centimeters as well then. Draw a sketch of the optimum shapes. So now that we know that x is that, so we've got on the right, it was just x. So that would be 5.31 centimeters. Coming across here, so the answer times by 2 is 10.6. And then the height, so height was 200 over x squared from star. So if we work that out, so we've got 200 over 5.313292846 squared. So 7.08. All right, groovy. So in theory, what should happen is if I times all three of those numbers together, So 10.6, 5.31, 7.08. They should all times up to give me 400, which they do minus some weird rounding stuff. You can also see why rounding is so important, because even though I rounded off each of those numbers to some decimal places, the actual answer is off by about 2. And that often happens with rounding, so you got to be really careful. Okay, kinematics, calculate S of 2. So S of 2 equals, now I'm just going to get this graph straight away because almost always in kinematics questions, you're going to want a graph of this thing. So 30x take 4.9x squared. All right, so let's fix our window. So 0 to 10 or 8 maybe, and then 0 to 20. See if that does it. Y needs to come up a bit, so maybe 0 to 40, and I might actually look at some negatives for Y as well. The ball will not fall underneath the ground, but just so we can get an idea of where these x-intercepts are. More Y would be good, so maybe let's go up to 60. There we go. Trace to enter 40.4. Meters. So 2 seconds since the kick. Yeah. Differentiate S of t to find the velocity. So the velocity is just the derivative. So that's 30, take 9.8 t. We're going to solve 0 equals v of t to find the max height. That's always what you do. So in other words, we're trying to find this maximum, so stationary point. It should be at 3.06 as the t-value. So 0 is 30, take 9.8 t. So therefore 9.8 t is 30. Therefore t is 30 over 9.8. And if we work that out, we should get about 3.06, which we saw before. 9.8. Yeah. So t roughly equals 3.06 seconds. Use your answer from C to work out what the maximum height is. So S of 3.06 roughly equals, and then we go back to our graph. So whenever I work out these S values, you can actually sub it into the equation. So for example, that first one, I could have done 30 times 2, take 4.9 times 2 squared, and I would have got 40.4. But it's just a lot quicker to do it on your graph with trace. So let's draw that. We're going to trace, well, actually, I might just go G solve max, not min, max. Try that again. 45.9. So that is the max height. Okay, now we've got this general conjecture sort of thing. Previously, that number was 30, but it could, in theory, be anything. So here we go. Let's look at some more graphs. So what we want to do is change our graph to be 40 instead of 30. By the way, you can just solve the velocity equals 0, but I'm just going to do this on the calculator for now. Okay, so G solve max, we got 4.08, 4.0816, and 81.632. And then if we go for 50, so S of t is 50t take 4.9t squared, and the velocity is 50 take 9.8t. And we should get some lovely numbers when we plug in 50. All right, again, I need to bump up the window a little bit, so let's go to 200. And we want G solve for that maximum. 5.1020 and 127.551. Make a conjecture about the maximum height reached based on V0. So for example, if we work out, now this conjecture is actually kind of tricky to spot, so I'll show you how you might actually prove it. In general, S of t is V0t take 4.9t squared. Therefore, the velocity is v naught take 9.8 t. We want the velocity to equal 0. So therefore, 0 is v naught take 9.8 t. Therefore, 9.8 t is v naught. Therefore, t is v naught over 9.8. Done. So that's actually what the conjecture is. So if S of t is v naught t take 4.9 t squared, then max height is at t is v naught over 9.8. Now, let's check that we're correct. So our first one was 30 over 9.8, and yes, that gives us 3.06. The next one should be 40 over 9.8. Yes, that gives us 4.08. The next one is 50 over 9.8. And wouldn't you know it, gives us the correct number there for the table. If a footballer wants to kick a ball to a maximum height of 150, what initial vertical speed will they need to kick the ball with? All right, so first of all, look at our table. It goes up to 127 there. So I would assume maybe a bit more than 50. So let's think about our y value. So S of t is v naught t take 4.9 t squared. I might actually put here when v naught is greater than 0. So S of that t value, so v naught over 9.8, is v naught times v naught over 9.8. Take 4.9 lots of v naught over 9.8 squared. That's going to be a lot to deal with, but we'll get there. So we want that to equal 150. We'd like that point to equal 150, the position. So this is v naught squared over 9.8 take, well, let's think about what 4.9 times, forget about the v naught, but 9.8 squared is on the bottom. So that whole thing becomes 5 over 98. 5 v naught squared over 98. Okay, so if we think about this, this is all got a common factor of v naught. Well, v naught squared actually. We can work out what that is. So 1 over 9.8 take 5 over 9.8 gives us that number, which we might want to get back as a fraction. So minus 20 over 49. V naught squared is 150. Therefore, v naught squared is 150 divided by that number. So if we look at 150 divided by the answer that we just got, my mistake. I was going to say a negative number is not what I wanted. One over 9.8 take 5 over 98 should have been 5 over 98 there. My apologies. And so this should be 5 over 98 here. Hopefully, that gives me a nice number. Let's see. Tuning 2940, but let's just make sure our calculator hasn't done something weird. Yeah, 2940. V naught squared is 2940, therefore V naught is root of 2940, so V naught is roughly 54.2 meters per second. Now, how are we going to check that we got this right? Let's graph it. So in theory, if I go 54.2 and I draw this all up and I find my maximum, I'm really hoping the maximum height, 149.8. minus some rounding is 150. Remember, rounding can sometimes blow up into bigger issues. But yeah, so that's how high the ball goes. And that is the end.